Okay, now let's say we want to use the inverse or computing the inverse of a matrix to solve a system of equations. So say solving a system of equations using inverses. Now, if we'll remember, let's say we have like a11 x1 plus et cetera, plus a1n xn equals b1 all the way down to am1 x1 plus et cetera, amn xn equals bm. If you remember, this is a system of m equations in n variables. And we knew that there was a coefficient matrix given by A equals A11, AN1, 1N, AM1, AMN, right? And we had the vector, the column vector x, which was composed of the variables x1 through xn. And then we also had the vector b representing b1 through bm here. And the matrix form of this system of equations was given by ax equals b, right? If you were to compute, and we did this in a previous video, if you were to compute the product x or ax, you would get the right-hand side of the equations here, right? It'd be listed as a column vector where each entry, like the first row was the first equation, et cetera, and then that product equal to b. Well, then we said solutions to this system of equations is just finding the entries of this column vector, right? If we could find the entries x1 through xn of this column vector x, then we would have the solutions to this system. Well, now we know how to compute the inverse of a matrix. And so if you have a system ax equals b with a invertible, so with a invertible, then what could we do? Well, then we could take A inverse and multiply by A inverse on the left. And whatever you do to one side of an equation, you have to do to the other, right? And technically, this would be A inverse times the product AX, but matrix multiplication is associative, so we would get A inverse times A times X equals A inverse B. And then we would have X equals A inverse B. This then, well, A inverse, this is the inverse of your coefficient matrix. And then B was whatever this column vector was on the right-hand side. Well, then you just have to take a product of two matrices. And then immediately what you have is, this is your solutions, right? These will give you the solutions to your system of equations. Just all you have to do is compute this product, A inverse times B. And so I won't in depth go through an example, but I'll walk through what one would look like. Let's say we have the following system. X minus z equals 1, x minus y plus z equals 3, and then x plus y minus z equals 2. Okay, now we know what our coefficient matrix would be. A would be 1, 0, -1, 1, -1, 1, 1, 1, -1. Our column vector of possible solutions would be x, y, z. And then B would be the column vector on the right-hand side. So 1, 3, 2, right? And let's set up AX equals B. That would exactly represent this system here. So what we would have is, excuse me, 1, 0, -1, 1, -1, 1, 1, 1, -1 times x, y, z equals 1, 3, 2. Well, what we would have to do is we would have to compute the inverse of the matrix A here. And I'll leave this as an exercise. It's a relatively simple matrix to compute the inverse of because of all the ones. You get that A inverse is equal to 0, 1/2, 1/2, 1, -1, 0, 1, -1/2, -1/2. Okay, and then so if we were to multiply both sides of this equation here, if we were to multiply both sides of this equation by A inverse, what would we be left with? Well, we would be left with XYZ equals, and then we multiplied B on the left by A inverse here. So A inverse times B, 1, 3, 2, and a relatively quick computation there of the matrix multiplication, you can see what you would get is the vector 5/2, -2, -3/2. And so this would already be our solution to this system. So this is an example of, and again, I'm skipping actually computing the inverse because I've gone through an in-depth example of how we compute the inverse. So you would have to go through that process again. But luckily, since this matrix A is relatively simple with just ones, -1s, and zeros, hopefully you can compute this matrix inverse relatively quickly. And then this product is pretty simple, right? You can see for the top one, you would have 5/2, and then -2, and then -3/2, right? And so this is an example here of how you can solve a system of equations by calculating the inverse of a matrix. And remember, this only works if A is invertible, right? And so we need to be careful about the invertibility part. Now, I want to list some properties here. This is listed in the textbook as a theorem, so keep that in mind that all of these would require proof. But I want to list some properties relating the transpose to the matrix inverse, right? We've talked about both of these things kind of separately. Let's look at some properties of these in juxtaposition. So if we have the transpose of a matrix and then we're to take its inverse, well, that's the same as first taking the inverse and then computing the transpose. We have a property that says if you take the inverse of the product AB, then that's the same as first B inverse A inverse. And so when you kind of distribute this inverse, if you will, the order of the product flips, right? So that's always important to keep in mind. This is true for like finite products as well. So if you were taking like a product of K matrices, A1 through AK, and then taking the inverse, well, this is, you always flip the order. So AK inverse, AK minus 1 inverse, et cetera, all the way down to A1 inverse. We have that the inverse of an identity matrix is always itself, right? And this one's not too hard to prove. So maybe you could see what to prove. And there's really nothing to prove actually, because how would you calculate the inverse of 1, 1, 1? Let's say for 3 by 3 example. Right? Well, we already have the identity on both sides. And so basically what we have here is IN augmented IN. This is kind of the trivial case for computing the inverse. You see, you already have, like in the non-trivial case, you have to pass from the identity matrix on the right-hand side to get it on the left-hand side, but it's already on both. And so we see that the identity is its own inverse. For the next property we have, and I think we talked about this property for transpose, but it's true of matrices or matrix inverse as well, is if you take the inverse of the inverse, you get back the original matrix, right? And that's The proof of this would just be to compute, like go through our algorithm, compute an inverse of a matrix, but then just flip the page upside down and read your work backwards, and you would be getting from A inverse back to A by taking the inverse, right? Okay, we have a few more properties here. We have that if you have a product of A, so you're taking A times A, K times, well, then if you take the inverse of that power, this is the same as first taking the inverse and then raising the inverse to the kth power, or taking the product of all of these inverses first. The last one I want to talk about is if you have a non-zero scalar P and an invertible matrix A, then PA inverse is the same as 1 over PA inverse. So you invert the scalar as well there. And this can save some time if you find, like if you find a common factor in your matrix A and you want the simplification process to be easier, well, you pull that common factor out so the numbers are simpler in the matrix, right? Then you go through your row reduction, and then you know whatever A inverse is, well, you just multiply by 1 over whatever you pulled out front of the matrix A. And to wrap this up here, and then we can talk about elementary matrices, I want to state the following theorem. We have the theorem that says A is invertible if and only if, so this IFF here, this means, whoops, I'm already recording, thank you. This means if and only if. So if you ever see me write I with, or if with 2 F's, I'm not crazy. I'm writing if and only if, right? So A is invertible if and only if the reduced row echelon form of A is the identity. Okay, so this is one way to check, like if you were to solve a system of equations, you're like, well, I know this only works if my coefficient matrix is invertible. I don't want to get myself in trouble by doing all this work and then finding out that my matrix wasn't invertible. Well, now we have a way of checking, right? Just if you can get your matrix A to a reduced row echelon form of the identity matrix, like just ones along the diagonal, zeros everywhere else, well, then you know it's invertible. And you've probably already also done some of the work because you've gone through these row reduction steps, right? So we do have a way of checking if A is invertible before just kind of blindly diving in and hoping that something's invertible when solving a system. Okay. Lastly, for the week, I want to talk about elementary matrices. So what is an elementary matrix? We'll brilliantly denote an elementary matrix by E, and these are square matrices. So n by n matrix here. And let's give a definition. E is an elementary matrix if it is the result of applying only one row operation to the identity here. So the elementary matrices are a specific family of matrices that you start with the identity with ones along the diagonal, zeros everywhere else, and you make one move, right? You make one row reduction or one operation or whatever. These are called elementary matrices. If, in particular, if E is the result of switching two rows of IN, we say E is a permutation matrix. Okay, so for example, an example of a permutation matrix would be something like, well, what's the identity? Like I3 is 1, 1, 1, 0, 0, 0, 0, 0, 0, right? Then P, and we could write it like P1, 2 that swaps rows 1 and 2. This permutation matrix would be 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, right? This would be an example of an elementary matrix because we've performed one operation here. The only thing we've done is swapped row 1 with row 2. And so you could think about like Pij. This is the elementary matrix where rows I and J were swapped. Let's say are swapped. Rows I and J of the identity matrix are swapped. Okay. We also have another example of elementary matrices as we'll denote them as like EKI here. This is where you multiply the ith row of I sub n, the identity matrix, by scalar k, right? So for example, we have E5, 2 would be like for a 3 by 3, right? Let's say we're looking at I3 here, which is 1, 1, 1, 0, 0, 0, 0, 0, 0, right? E5, 2 would then be, well, the only thing we did was we multiplied the second row by 5, so 0, 5, 0, 0, 0, 1. And so this is another example of an elementary matrix. And these kind of permutation matrices and these EKIs are among the most common that we'll see. I want to quickly go over an example and kind of describe where elementary matrices can come into play. So let's say A is a matrix obtained, or rather, let's go the other way. Let's say B is obtained from a matrix A by one row operation. Okay, so then if E was obtained from I, like say IN here, if E was obtained from I by the same row operation, then EA equals B. And so you can use elementary operations, or elementary matrices, excuse me, to kind of represent B as a product of how it was obtained from a previous matrix. And so let's see an example to make this a little less confusing. Let's say A is the matrix A, B, C, D, E, F. So we have a 3 by 2 matrix here. Then let's say we have B is the matrix C, D, A, B, E, F, right? And here you can also see what B was obtained from A. How was B obtained from A? Well, we flipped row 1 with row 2, right? This B was obtained from matrix A just by swapping row 1 and row 2. So now let's take the matrix E, which is the result of swapping row 1 and row 2 of the 3 by 3 identity. So like 1, or excuse me, this would be 0, 1, 0, 1, 0, 0, 0, 0, 1, right? This is also what we called like P1, 2 here. This is obtained from the identity matrix by the same row operation, right? And that's what I was saying here. It's by the same row operation. Well, then what is E times A? Then we have 0, 1, 0, 1, 0, 0, 0, 0, 1 times A, which is A, B, C, D, E, F. Now let's compute this product. If we compute this product, well, in the first we start with the column ACE, put it up here, right? We'll see for the first entry, we get C. Do the same thing for the second column, we'll get D. And then we go to the second row. So we'll have A times 1. For the second column, we would have B. And then for the third, we would just have E and F. And so here we've verified that EA equals B. And so if you've obtained A from B by some row operation, you can actually recover what the elementary matrix was there. And you'll see some of these examples on the homework is like, okay, well, if you know that B was obtained from A by this row operation, then how can you express B as the product of A with an elementary matrix, right? And so we'll see some examples like this on the homework. And this gives us kind of a pretty solid introduction to matrix arithmetic and a bunch of operations that we can perform on matrices, how we can use these to solve systems of equations. And where we'll go from here is we'll still be looking at matrices very heavily, but the next topic is LU factorization. And we'll have this notion of a lower and upper triangular matrix. And then we'll start to look at how we can express matrices in terms of the products of these upper and lower triangular matrices. And so we'll still be dealing with matrices quite a lot, but just kind of a teaser is where we're going from here.